Welcome back to Physics 142. We've been talking about capacitors, these devices and circuits that store electric potential energy. And I want to talk through an example here that hopefully helps develop your intuition a little bit more about capacitors and how they work. So you might remember that for capacitors, the equations that we have are we define the capacitance of a capacitor, its ability to store potential energy, as Q divided by V, the amount of charge Q that gets put on the capacitor divided by the potential difference across that capacitor. We also realized that we could write the capacitance as just depending on the geometry of the capacitor. So for a parallel plate capacitor where you just have two metallic plates, we realized we could write it as the area divided by the distance between the two, the area of each plate divided by the distance between the plates, and then you end up with a factor of epsilon naught. So the situation that I want to think about as we develop our intuition over here is, let's consider a circuit where we've got a power supply or a battery that supplies a potential V. So that means that if down here you have no potential, if you go through the battery, if charge, what the battery does or the power supply does is it means that up here you're on top of the hill. So going through the battery is kind of like climbing the hill. You end up with lots of potential V up here at the top. All right, so up here at the top, you have a potential V. And then we'll imagine that this particular circuit has a switch in it. So first we'll close the switch and let this capacitor get charged up. So some charges will flow off of the battery here, and you'll get a charge plus Q up here on the top of the capacitor. And if the top of the capacitor has charge plus Q, then that means to balance, you end up with charge minus Q down here on the bottom of the capacitor. And then what I want to do is I want to break the circuit. So we're going to take and we're going to open the switch. This is a symbol for a switch in a circuit. So we're going to open the switch, and that means that the charge can't flow anymore. All right, once you break a circuit, then charge can't flow in the wires anymore. So now this capacitor over here is essentially isolated. And what I want to think about is, let's suppose that there's some distance d between these two plates, and I want to think about what happens if we increase the distance between those two plates. What's going to happen to the capacitance? What's going to happen to the amount of charge on the plates? And what will happen to the potential across that capacitor? So, well, let's think about this. Think about what's going to happen. So if we increase D, we said the capacitance, it just depends on the geometry. So if we make D get bigger, all right, if we increase D, then that means that the capacitance is going to have to go down, right? Then the capacitance has to go down. So C is going to go down if D gets bigger. It's going to be less able to store potential energy. Okay, that's all well and good. So we now know what happens to the capacitance from this equation. Well, what about the amount of charge on the capacitor? Well, if the wire's broken and no charge can flow, then, so if it's disconnected, then no charge can flow, then the charge just has to stay, right? Then Q is just going to be constant on that capacitor because it's broken. No charge can flow on or off, so Q is constant. And so what does that mean about the potential? Well, let's think about that. If we look at this equation here, solve it for potential. Potential is going to be Q over C, right? That's rearranging this equation algebraically. And so Q is constant and C is going down. So what does that mean about the potential? It means the potential then is going to have to go up. And specifically, if let's say I doubled the distance between the two, that would make the capacitance get halved. And if the capacitance was halved, then the potential would get doubled. So interestingly here, the potential, you end up with the potential increasing and the capacitance going down because Q is constant. I'll just make a side note that we said that the electric field in this capacitor, remember there's some electric field in this capacitor, and what we worked out in previous videos is that that electric field is constant and for a given charge. And so if the charge is constant, then that means we had that E was sigma over epsilon naught. And so if sigma, which is charge per area, if area and charge are both staying the same, then the electric field stays the same. So the potential is going up because remember potential is electric field times distance. And so if we increase the distance between the two but keep the electric field constant, it makes sense that our potential also increases as well. Good. All right, now I want to show you though that the situation is a little bit different if instead we have the circuit and we just keep the circuit closed. All right, so now we're again going to take and we're going to charge up the capacitor originally to plus Q and minus Q. All right, and again have a distance D between those two plates. But now I'm going to keep it connected and increase the distance between those two plates. All right. So again, just like before, the distance, if the distance goes up, the capacitance has to go down, all right? But now, what's constant? Well, the charge on these plates, the charge could change. The thing that's constant across these plates is that when you're connected to the battery holds this region at a potential V, at a high potential, and this region down here, it gets held at no potential. That's no potential. So this potential difference across the capacitor, as long as it's connected to the battery, has to stay V. It has to be an amount V. So in this case, delta V, or the potential across the capacitor, the potential drop across that capacitor, has to be a constant. Well, now we see that if the capacitance is going down and delta V is constant, if we think about the Q must be C times V, right? And if V is constant and C goes down, then that means that Q also is going to have to go down. So we get that if the distance doubles, the capacitance halves, then the amount of charge on each plate also would have to halve. So you end up getting a different behavior depending on whether or not this capacitor is attached to the battery and then thus held at constant potential, or whether it's disconnected and just has a certain amount of charge on it.